Hello everyone, welcome to my class. In today's class, I'm going to cover section 13.4, motion in space, velocity and acceleration. Let me start the class right away. The first definitions. Velocity of a particle we denote by Vt equals to the derivative of position functions, that's r prime t. Acceleration of a particle we denoted by vector at equals to the derivative of velocity or second derivative of position function. Speed of a particle, which we denoted by simply v without the vector sign, that's the magnitude of vt or magnitude of the derivative of position functions. Great. Quick fact, we know a vector of constant length is perpendicular to its derivative. That means that for a constant speed, velocity and acceleration are orthogonal. Moreover, for a circular motion, the acceleration points toward its center. In the circular motions, the acceleration always points towards the center. Here's a quick proof. Consider a circular motions given by r equals to cosine pi t sine pi t. Take the derivative of r, find the magnitude of r prime, which is pi, means so we have a constant speed. So next, acceleration equals to second derivative of r, which turns out to be negative pi square the positions functions, negative pi square rt. So that means opposite directions of the position vector. So the accelerations points inside toward the center of the circular motions. Great. Quick note. Great. Quick note. If you throw an object upward and observe the motion at its maximum height, there, even if velocity is 0 but accelerations cannot be 0, in the T and B frame, acceleration lies in the plane of tangent vector and normal vector. So let me summarize the T and B frame here. That's the space curve. The unit tangent vector points the direction of the flow and points the directions where the curve is turning into. So this is the n directions, and this is the binormal directions, which is simply t cross n. And accelerations lies in the plane containing t and n. So accelerations is in these directions. Acceleration has two components: the tangential component denoted by at and the normal component denoted by an. I showed you in the picture here. So this component is at, means this component is at, and this component is an. So this is the horizontal component of acceleration, this is the vertical component of accelerations. Then we write acceleration equals to at unit tangent vector plus an unit normal vector, and where at equals to scalar projection of A onto T, scalar projection of A onto T, which turns out to be simply A dot T. Similarly, the normal component an of accelerations equals to scalar projection of A onto n, which is simply A dot n. In other words, it turns out that the tangential component of accelerations is the rate of change of speed, and normal component of accelerations turns out to be curvature times the speed square. Quick note, consider a passenger in a moving car. A sharp turn in the road implies a large curvature. That implies the normal component of acceleration is greater than the tangential component of accelerations. So the passenger is thrown against the car. Sometimes the following equivalent formula is simpler to compute the accelerations where AT can be computed by this ratio r prime dot r double prime over magnitude of r prime, and the normal component of accelerations an equals to the ratio the magnitude of r prime cross r double prime over magnitude of r prime. I hope this makes sense to you all. Now let's move on. So next, let's talk projectile motion in 2D and trajectory in 3D. So that means we are throwing some object standing here upwards with initial velocity v0, making an angle theta with the ground. Then the object attains some maximum height and lands on the ground again after a certain time. So let's find this projectile, or let's find the position functions. Let's find the position of this object as well as the distance how far it lands on the ground. So set up in 2D, set up the axis in such a way that the projectile starts at the origin with an initial velocity v0, and we know acceleration equals to at equals to 0 comma negative g. Then integrate. This gives us a velocity. This c is the constant of integration, which is the vector here. So at t equals to 0, let's compute the value of c vector. C vector, it turned out to be the initial velocity. So then we get our v equals to v0 minus gtj. Again, integrate the velocity. It gives us the rt, the position vector. And to find the value of this constant vector d, we put at t equals to 0, then r0 turns out to be, this is 0, this is 0, so simply the 0 vector, which is d. Then put the value of d, which is 0 vector here. Then we got the position of our object is v0t minus 1/2 gt square j. Now in parametric equations for this projectile, here rt equals to the v0 vector is with this component here, v0 cosine theta comma v0 sine theta, let me use this one, times t minus 1/2 gt square j. And simplify, this gives us this form here, v0 cosine theta times t comma v0 sine theta times t minus 1/2 gt square. So the projectile reaches the ground when y equals to 0. That means this y component equals to 0. Simplify, this gives us the time t equals to this number 2 v0 sine theta over g. So the distance is simply the x component. So then distance equals to xt, t equals to this number. Simplify, this gives us distance equals to v0 square sine 2 theta over g. I hope this makes sense to you all. Similarly, to get the maximum height reached, we need to set y prime equals to 0, solve it for t, and then compute yt. Awesome. Now similarly, let's work in 3D case. The result follows analogously as follows. Suppose the initial position is r0 with component x0, y0, z0, and initial velocity is v0 equals to the vector with component u0, v0, w0. Then again start with scratch. The acceleration equals to negative gk, that's the vector, 0, 0, minus g. Then by successively integrate, so integrate acceleration gives us velocity, and integrate again velocity gives us the position vector rt. This is the final form, which is the trajectory. Now to find the location where the object lands, we set this time as gt equals 0 in xy plane. So set gt equals 0, solve for t, and substitute the value of t back on x component and y component. That's the idea here. I hope this makes sense to you all. So let me make one final comment. You don't need to memorize this formula. Always start from the scratch, the accelerations formula, and then take the integrations, find the value of the constant, the vector constant, and accelerations. First integration of acceleration gives you velocity. Take another integration of velocity, gives you the position vector. So that's the idea. So in the 2D case, start from here and derive all these things for the actual problems, and for 3D case, start from again the accelerations and find out respective formula. I hope this makes sense to you all. Now let's do some example. First example, consider the helix given by the vector functions rt equals to the vector 3 cosine t, 3 sin t, 4t, and find the tangential component of accelerations and normal component of accelerations for the helix. Here the formula at is given, an is given. So now let's find the first derivative of r, second derivative of r, dot product of r prime and r double prime, and cross product of r prime and r double prime, and substitute here. So just the routine computations. Here r prime t, find its magnitude, turns out to be 5. Find r double prime t and take the dot product of r prime and r double prime. So that means we are taking the dot product of r prime and r double prime. That means we are multiplying the corresponding component and adding them. So here multiply this component. So minus 3 sin t times minus 3 cosine t plus 9 sin t cosine t. Second component, 3 cosine t times minus 3 sin t equals to minus 9 cosine t sin t. So this cancels to the first term. And then the third one here, 4 times 0 is 4. That's why the dot product is 0. Similarly, compute the cross product r prime cross r double prime using 3 by 3 determinant. First row I, j, k. Second row the component of r prime. Third row component of r double prime, and expand the 3 by 3 determinant, which turns out to be the vector here, whose component are 12 sin t, negative 12 cosine t, 9. Find the magnitude of r prime cross r double prime, which turns out to be 15. Hence, the tangential component of acceleration is dot product 0, means the numerator 0 means 0. That's why the answer is 0. And normal component of accelerations is 15 over magnitude of r prime is 5 is 3. I hope this computation makes sense to you all. Now let's move on. Example 2. A particle moves with the position functions given by rt equals to the vector t, t square, 3t. Find the tangential and normal component of the accelerations. Begin the solutions. First find r prime t. We can easily compute the derivative here, right? The derivative of t is 1, derivative of t is 1, derivative of t square is 2t, derivative of 3t is 3. Find the magnitude of r prime t. Turns out to be under the radical 10 plus 4 times t square. Similarly, find the second derivative of r, which is simply 0, 2, 0. Compute r prime t dot r double prime t. Compute r prime t cross r double prime t and compute its magnitude. Turns out to be radical 4t. Then by formula, at equals to 4t over under the radical 10 plus 4t square, and an equals to radical 4t over radical 10 plus 4t square. I hope this computation makes sense to you all. Now let's move on. Example 3, the projectile motion. An athlete throws a ball at an angle of elevations pi/4 above the horizontal with an initial speed of 30 meters per second. Answer the questions A to B. A. What is the position function of the ball at time t? B. Where does the ball hit the ground? I hope this question makes sense to you all. Now let's begin the solutions. So here V0 equals to 30. So the initial velocity equals to V0 cosine theta, V0 sine theta. By the way, theta is pi/4. So the initial velocity turns out to be the vector 15 radical 2, 15 radical 2. Also, the initial positions are 0 turns out to be the 0 vector. Initially, he's in the ground. Now, start from the scratch. So we know acceleration equals to negative gj. So for our simplicity, let's take g equals to 10. Then integrate the accelerations. Then to find the value of this c, evaluate at t equals to 0. This turns out to be c equals to the vector 15 radical 2, 15 radical 2. Then substitute this back here. Then our velocity equals to vt equals to the vector with component 15 radical 2, 15 radical 2 minus 10t. I hope this makes sense to you all. Again, let's integrate the velocity. Then this gives us the position vector rt. Then find the value of this constant vector d. Hence our position function is rt equals to the vector with component 15 radical 2 t, 15 radical 2 t minus 5 t square. I hope this makes sense to you all. So this is the position functions we are looking for. Next, let's find where does the ball hit the ground. So that means I need to put this y component equals to 0, solve for t, and substitute the value of t on the x component. That gives us the distance. So set yt equals to 0. That means 15 radical 2 t minus 5 t square equals to 0. So factor the 5t out. So then 5t times 3 times radical 2 minus t equals to 0. Since time is not equals to 0, t not 0, so the inside equals to 0 means t equals to 3 times radical 2 second. Then put t equals to this value back on the x component. Hence the distance equals to 15 radical 2 times 3 radical 2 turns out to be 90 meters. I hope this makes sense to you all. Great. Now let's move on. Now example 4, the trajectory. A constant force F with magnitude 20 Newton acts directly upward from the xy plane, means toward the z direction, on an object with mass 4 kg. The object starts at the origin with initial velocity with component 1, -1, 0. Find its speed and the position functions at time t. So let's begin the solutions. To begin the solution, assuming that a resistance is negligible and the only external force is due to gravity. So here magnitude of force is 20 n along the z-axis, so force equals to 20 k, also mass equals to 4 kg. So now start from the scratch. So we know force equals to mass times the accelerations, Newton's second law of motions. Then accelerations turns out to be 20 divided by 4 is 5 in the direction of k, which is the vector with component 0, 0, 5. Now let's integrate. Let's integrate the acceleration. It gives us velocity. Then to find the value of c, evaluate at t equals to 0. This gives us c equals to the vector 1, -1, 0. Substitute back the c value here. Then it gives us the velocity v equals to the vector with component 1, -1, 5t. I hope this makes sense to you all. Consequently, the speed equals to the magnitude of velocity, which turns out to be under the radical 2 plus 25 t square. It depends on t. Awesome. Again, integrate the velocity. It gives us the position vector. And with routine computations, it turns out the position function is rt equals to the vector with component t, -t, 5 t square. I hope this makes sense to you all. So we finish these sections 13.4 as well as we finish the chapter 13. So next time, so we'll start chapter 14. Thank you.